is on joining extractions of regular expressions, and Liat will give the talk.
Okay, can you hear me? Great. Good afternoon. My name is Liat, and I'm going to present the paper Joining Extractions of Regular Expressions. This is a joint work with Dominique Friedenberger and Benny Kimmelfeld. Okay, so I'll start with giving the basic motivation. So nowadays we have lots of applications that are based on text-centric data. And traditional database systems know how to deal with structured information, yet they give limited support for text analytics. So therefore, usually we take the text, we obtain structured data from the text, and this is information extraction. So information extraction is a task of obtaining structured data from textual data. So in order to understand IE systems, we have the framework of document spanners. And you already heard about document spanners in the previous talk, so I'll describe briefly what document spanners are. So we have a document, which is simply a string. Okay, the numbers underneath the strings is just for convenience. We have a span. A span is a pair of numbers, and this pair of numbers corresponds with a substring of the document. And we have a spanner, which is simply a mapping that maps an input document into a relation. Okay? For instance, we have this NLP function. This NLP function extracts the verb and its corresponding preposition. Okay, so this is a spanner, and what's different in spanner is that the output relation, the entries of the output relations are no longer strings as it used to be in the relational model, but we have spans. So what's the natural way to represent spanners? So a very natural way is by regex formulas. Regex formulas are extensions of regular expressions. So here's a regex formula. We call it gamma of z. So this is the regex formula that have the variable, the capture variable z. And you see that z captures part of the regular expression. And this is a mapping. This induces a mapping. How does it induce a mapping? We match the input string into the regex formula, and then we obtain an assignment for the z. And each tuple corresponds to a matching. Okay, so this is a document spanner, and we can have regex formulas with more than one variable, for instance, gamma of x, y, z, and so on. So this is regex formulas. This is a basic way to represent document spanners. And a natural extension is to add relational algebra operation. And the operation are projection, join, and unions, as you know from the standard or the classical relational model. So for instance, when we join two span relations, we obtain this relation. Okay, so this is the class of regular spanners. And what we try to do is we try to study the complexity of regular spanners. So let's stop for a while and go back to the relational model. In the relational model, we had conjunctive queries. Conjunctive queries are evaluated on a database, and the output is a relation. Okay, so we have such a conjunctive query, which is a projection of joins, and we evaluate it, and that's it. In our case, the conjunctive queries, the basic building blocks of the conjunctive queries are no longer relational atoms, but now are regex formulas. So we have joins of regex formulas, and we take their projection on them, the projection on some variables. So you can see here is the example, and the input for such a query is no longer a database, it's a string now. Okay, so And what's the semantic of such an expression? The semantics of such an expression is obtained by looking at a document, evaluating each of the regex formulas on the document. When we evaluate each of the regex formulas, we obtain a span relation. Then we have a database with special relations, and what's special in the relation, what's special is that the entries are spans, and we evaluate conjunctive queries on this database and obtain the result. Okay, so this is regex CQs. In general, regex CQs are expressions of this form. We take joins of regex formulas and we project them on some of the variables. And what what the paper tries to do is to study the complexity of evaluating regex CQs. So when we talk about complexity, we have data complexity and we have combined complexity. So the picture for data complexity, in data complexity we fix the query and we look at the document as the input. And in this case, the evaluation can be done efficiently. And why is that? So it's an intuitive explanation. We just need to match the variables on top of the input string, and we can do it in polynomial time. The work in data complexity, you will soon see here a talk about constant delay algorithms for document spanners. And we have a work about recursive programs for document spanners, which also study the data complexity, and it's going to be presented in the next ICVT. So in this paper, we study the combined complexity. In terms of combined complexity, the input is both the query and the document. Okay, so both regarded as the input. So what's the most naive thing we can do when we want to evaluate the regex CQ on top of a document? The most naive thing we can do is, as you already saw, we can take the document, evaluate each of the regex formulas on the document, and obtain a database with span relations, and then take the conjunctive query and compute it on top of this database. This is the most naive solution we can think of. So in order for this process to be efficient, we need the first step to be efficient, to be done efficiently, which is the evaluation of each of the regex formulas on the input string. And we also need the second step to be done efficiently, which is computing the relational query. Okay? So we have the following theorem. The evaluation of regex CQ is in polynomial delay if, 1, the regex formulas produce polynomial time of answers, and 2, the CQ is from a tractable family. So the first condition talks about the first step. So if the regex formulas produce a polynomial number of answers, we show that we can find an algorithm that produces these answers efficiently. So we're okay with the first step. And for the second step, there's a lot of research that was done about conjunctive queries, and we use it. And we, for instance, if the underlying query is acyclic, we know that we can compute it efficiently. Okay, so this gives us two conditions in order for this approach to give us a good algorithm, efficient algorithm. So a small thing, I'm talking about polynomial delay. And why is that? So I'm talking about polynomial delay in terms of efficiency because the output relation might be exponential in the input. Okay, and since the output might be exponential in the input, I have to define what efficiency means. So I'm talking about polynomial delay. So now one might ask, okay, do you really need those two conditions, or you can be okay, or one is sufficient? So the answer is that I really need those two conditions when I choose the first approach. And in particular, we showed that the following are NP-complete. So the first is evaluation of CQs over ternary regex formulas. So if we relax the second condition, and we only give a restriction on the regex formulas, we face an NP-complete problem. Also, if we relax the first condition and we have the underlying query is inefficient, then we face an NP-complete problem. So the evaluation of a cyclic regexecq is NP-complete. Okay, so we really need those two conditions in order for the first approach to be giving us a good algorithm, an efficient algorithm. So, okay, so let's think of a new approach, a better sophisticated, more sophisticated approach. So the more sophisticated approach is via automaton. So I'll present what's vset automata. So vset automata is an alternative way to define document spanners, specifically regular spanners. Vset automata are non-deterministic finite automata with transitions that open and closes variables. And we can look at regex formulas and close them under union, join, and projection. And this is equivalent to look at this model, which is vset automata. And why do we want to look at this model? Because we know and we show that we can enumerate the tuples of A of S with polynomial delay. So what's A of S? So A is an automaton that represents a regular spanner. And A of S is the evaluation of the spanner on S. So when we have the automaton representation of the spanner, we can enumerate the result efficiently. Okay? So this leads us to the second approach. And the second approach says the following. Take the regex formulas, take the relational algebra operation, and compile everything into an automaton, specifically into a vset automaton. And then you know that you can enumerate the results of the automaton, and we obtain the following. So regexecqs can be evaluated in polynomial delay if the number of joins is bounded. So if we can do this translation of the query into an automaton in an efficient way, we can obtain efficient results. We can do it efficiently if we have a bounded number of regex formulas. Okay, so this is for the second approach. So now, okay, so we have regexecqs and we know what happens with regexecqs, and now the question is, what happens when we add string equalities? So let me explain what string equalities are and why are they interesting. So we have the class of regular spanners, which are regex formulas with union, joins, and projections. We have the class of core spanner, which is strictly more expressive than regular spanners. And core spanners add the operation, the string equality predicate. The string equality predicate checks whether two spans corresponds to equivalent substrings. And when we add the string equality predicate, we can express more than we could express without the string equality predicate. And conjunctive regexecqs with string equality predicates are defined this way. So we have joins of regex formulas. The basic building blocks are regex formulas. We have joins. Then we have sequence of string equality predicates. And we have a projection on top of everything. Okay, so this is regexecqs with string equalities. So we want to understand how does the complexity change when we add these string equality predicates and whether it changes. So let's see what happens in our two approaches. What happens to our two approaches? So the first approach, let me remind you, relational evaluation. We take the document, we take each regex formula, we compute the relation that is obtained by applying this regex formula on the document. We have a database that contains span relations, and we compute the relational algebra, the conjunctive query, and obtain the result. Now, what happens when we have string equalities? So fortunately, what we can do is we can add to this database the relations of the string equalities. Relations that contain tuples of spans that span equivalent substring. Okay? And then we can compute those relations in polynomial time, and therefore we obtain a similar result even in the case where we add string equalities. So we enhance the expressiveness, yet we get same complexity results. So let's talk about the theorem. So evaluation of regex CQ with string equalities is in polynomial delay. If one, the regex formulas produce polynomial number of answers, as it was without string equalities. And two, the CQ is from a tractable family. Now note that now the CQ is painted red. And why is that? Because now the CQ, we have to take into account the string equalities. So we treat the string equalities that we computed as binary relations. And when we look at the structure of the CQ, we look at this, those string equalities as binary relations that are part of the CQ. So this is for the first approach. So let's talk about the second approach. So for the second approach, we had an automata. We took the regex formulas and the relational algebra and compiled everything into the automaton. Now, what we want to do now, we want to take the string equalities and to also compile them into the automaton. However, this cannot be done, okay? So it's impossible to compile the string equalities into the automaton. So what can we do? So what we can do is compile the string equalities for a specific document. Okay, so if we, so in this case, we take the document, we fix it, we take its string equalities and compile everything into an automaton. And we can do that and obtain the following. So for every fixed k, regex CQs with k string equalities can be evaluated in polynomial delay. Okay, so if we can do the transition from the query into the automaton efficiently, then we can enumerate the result efficiently. And we can do that if we have a bounded number of string equalities. So this is for the second approach. So at this point, one might say, okay, so everything's good. We added string equalities, but we don't pay for it in complexity-wise. So I'm sorry to disappoint you. But when we talk about parameterized complexity, the picture changes, the complexity changes. And when we deal with parameterized complexity, we know that when we have regex CQ without string equalities, like a standard regex CQ, the evaluation is FPT delay with the parameter, which is the size of the query. Okay, this is in contrast to the standard relational model in which this is W1 hard. Evaluating conjunctive query is W1 hard with respect to the size of the query. When we add string equality, the complexity rises. Okay, we increase the complexity. And the evaluation of Boolean regex CQ with string equalities is W1 hard with parameter size Q. So we obtain that in terms of parameterized complexity, the complexity changes. Okay, so let me summarize what I just presented. So we studied the combined complexity of evaluating regex CQs. Regex CQs are conjunctive queries over regex formulas. So the basic building blocks are regex formulas, and we have relational algebra operations. So we study the combined complexity with and without string equalities. And again, string equalities are important and interesting because of the core spanner class. We presented two approaches to evaluating such queries. The first approach is the relational evaluation, is the naive approach, is obtained by computing each of the regex formulas and then computing the conjunctive query. And the second approach is compilation to automaton, and we explore the differences that arise due to the usage of string equalities. Thank you.
A string is a special case of a graph database, where you just have the nodes and the letters label the edges of the graph. There is a wealth of been studied in the database theory community about regular path queries and conjunctive regular path queries and union of conjunctive regular path queries and union of two-way conjunctive regular path queries, etc. Is there any connection to this view with the view that you would take if you look at the string as a graph database?
Yes, so Dominique can elaborate on this because the conclusion of our work was like the future work we saw is studying the complexity of CRPQs, and Dominique done it in his last work. So
Dominique, yes?
Dominique Freudenberger, which is a co-author, it is a joint work with him. So he.
What was the answer? I should talk to Dominique? What was the answer? I didn't understand the question.
Yes, the answer is that Dominique studied this case of a.
And what did Dominique find?
So I think it's better to.
Thank you.
I just don't want to miss anything, so.
Yeah, he's here.
So Dominique is here.
Too long.
Thanks. I just wanted to make sure I understood the setting without string equalities. So if I understood well, the first approach was tractable if I have a tractable CQ and polynomial number of results. And the second one is tractable if the query is constant size, right? So if I have a query which is tractable but not constant size, and I have spanners that give me exponential number of results, do you know whether it's tractable or not?
Again, if you have.
If I have a big CQ, but which is tractable, say it's a cyclic, for instance, and I have regex that will give me exponentially many answers, is this tractable or is it known to be intractable?
So we study the combined complexity, and therefore the number of. So in the first approach, you have to have a bounded number of regex formulas in order to be able to compute the conjunctive query efficiently. Sorry.
Yeah, we have a lower bound for this case. For the case of, we have the two conditions. The two conditions are necessary.
But when you do the first approach, right? Or they're necessary?
In the first approach, if you remove one of these conditions, then the problem is actually
Okay. So it's not specific to the first approach. I mean, it's a real hardness result no matter
it's a
how.
real hardness result. Under any of the two conditions alone, the problem remains empty.
Okay. Thank you.
So okay, you know that if we have a polynomial number of outputs and the CQ is tractable, then you have polynomial delay. So do we know anything, or do you know anything? If you restrict more the CQ to be in this free connect, say, cyclic class, right? So you have linear preprocessing and constant delay enumeration, and you still have a polynomial number of output. Do you get the same in data complexity, of course? So if the query is free connect acyclic and the regex formulas generate a polynomial number of outputs, do you get linear preprocessing followed by constant delay enumeration in data complexity as well?
So in two talks, they're going to talk about data complexity, and they're going to present constant delay algorithms in terms of data complexity for evaluating regex CQs. So I think this answers your question. So
You're in a better position to answer.
No, we don't talk about regulars.
It was a series. I want to know. So, I think we should stop here. So, let's thank Liat again.
thank you.